Hello, I'm Hugh Mannfield and welcome to my science channel. Now today I'm going to continue in another of my series of deeper dives into other videos that I've seen. And in this case we're talking about Dialect Philosophy and their video about Newton versus Mach and Newton's bucket experiment. Dialect does a great job of setting this up and defining the conflict between Newton and Mach, who Mach established Mach's principle, and Newton established the three laws of motion that we use today. To clarify the setup, I'll describe a little bit about what Newton's bucket experiment is about. Newton proposed that if you have a bucket of water, and Dialect shows it just sitting in space, but in the accounts I've read, Newton has it hanging from a rope. And you can start with the bucket at rest and the water within the bucket at rest, and it will have a flat surface. Now if you begin twisting the rope, you can bring that bucket up to a state of rotation. And the water within the bucket will slowly begin to rotate itself due to internal friction, and eventually it will come back to rest with respect to the bucket. However, this time it will have a concave surface due to the centrifugal action of rotating in the bucket. And what Newton said is that this allows us to define two possible states which appear identical if you are in a reference frame at rest with respect to the bucket. You will see a state where the water is concave, and you can see a state where the water is flat, giving us the ability to detect an absolute rest state in regards to rotation. In the video, Dialect gives the first round winner as Mach, because they say that you can only carry out Newton's bucket experiment in reference to a gravitational field, such as a planet would produce, like on the Earth. Well, I disagree, and there are ways to do Newton's bucket experiment in space devoid of any gravitational fields, and I'll explain those. So here we have Dialect's representation of the bucket in the gravitational field of Earth. And once again, we should imagine the bucket hanging from a rope that's attached to the handle. And in some of the accounts I've read, the experiment, the rope will just disappear into the distance, into the darkness above, and you won't be able to see the means by which it's being supported. So what you can do is, if we travel out into distant space, which is free from any nearby gravitational fields, so it's flat and uniform, we can construct a wagon wheel type space station. And then from the axis, from the hub, or actually any point lower on that station, we can hang the bucket from the rope. And then that bucket, which is at rest with respect to the wheel, if the wheel is in a state of rotation, it will have essentially a gravity field. Someone could stand on the rim and see the bucket hanging from the central axis. And if that rim is long enough, or the radius is big enough, the surface of the water in the bucket will be flat. If the radius is very short, you might actually be able to see that water is actually a curve that will match the curvature of the space station. But once again, let's make that radius long enough, and we'll see essentially a flat surface on the bucket. So now we begin to rotate the bucket, and the water in the bucket will come up to speed with the bucket. So in this state of rotation, you will have a concave surface on the bucket, and it may be skewed slightly to one side due to one side moving forward, having greater gravity, one side moving aft, having lower gravity, but you still will be able to see the two same basic states: bucket and water at rest with respect to each other, and in one case there's a concave surface, and the other case there's a flat surface. So This is how Newton's bucket experiment can be carried out in free space with no reference to any distant matter. And so Mach's principle is not required, and Mach loses round 1. So the next case they present is an update to Newton's bucket experiment in round 2, and they rightly give Newton the win. What they propose is that we put a spring between two masses, and if they're in rotation, that spring will stretch, and if we increase the rotation, it'll stretch longer, and if we decrease the rotation, it will become shorter, so that we can tell whether there's a state of absolute rotation. When it's at rest, the spring will be at its shortest distance. And I agree. Newton deserves the win. So then they go into a sudden death round 3. And they go into more detail about the mass on the spring setup. And what they claim at Dialect is that when you're actually at a state of rest, it's impossible to know the length of the spring at rest unless you remember back to another state where you could measure the spring before it was attached to the masses. And I say, well, no, this isn't necessary. If you set up multiple examples of these masses, you can have one that's rotating with an intermediate amount of stretch, and then get them all going that same direction at the same speed, so they all have the intermediate amount of stretch. Okay, now you increase the rate of rotation of one of them relative to the reference unit in the middle, and you will see either the spring stretch more or the spring will stretch less. Now, if you keep adding rotation in that same direction, if it's stretched more, it will continue to stretch more. If it's stretched less, it will continue to reduce until you reach a point where you add more rotation in that direction, it will begin to expand back outward. And this will give you the length when it's at absolute rest. Now there's more that you could do about this. When Newton proposed his two masses, he used a cord. So we can see that when you're in a state of absolute rest, the cord will become slack, and you'll be able to tell that. And this is probably why Newton, in his example, used a cord rather than a spring. Now there's something we have today called a bungee cord, and if Newton had known about them, he probably would have used one of those. But there are other things we can do to know when we're at the state of absolute rest in rotation in this kind of setup. First of all, rather than have the springs affixed rigidly to the weights, we could just put a hook on each end of the spring, which is usually what's done, and then an eye bolt or something on the end of the weight. And that way, when there's no force, when you're at absolute rest, the spring doesn't have any tension force on it, you'll be able to see that those hooks and eyes have no load. They become loose. So, prior knowledge is not required, and round 3 should rightly go to Newton. So in all cases, the problem Dialect finds with Newton's examples are really something they introduced. They changed from a cord to a spring, and then they complain that the spring requires some sort of past knowledge. Well, that's a problem they caused on their own, and I don't think Newton would approve of how they changed his setup. Had he been able to be here to defend, would be able to quickly refute their claims. So in all cases, Mach's requirement for the existence of outside matter or an outside reference fall flat. And in fact, even Einstein had to give up on Mach's principle, even though he used it early on in his development of general relativity. Now, the key to understanding why rotation has an absolute rest reference frame is understanding that rotation is a form of acceleration. And you can see my video on this in one of my earlier videos. Now, at Dialect, I believe they are big fans of Newton, and they're also pretty good fans of Mach. And Mach was okay in fluid dynamics, which he should have stuck with. He shouldn't have dabbled into the theoretical physics, at least in terms of Mach's principle. And for coming up with Mach's principle, I give Mach the dunce hat, because it's clearly demonstrable that Mach's principle is wrong. And in the end, it just reduces to playing mind games with labels. The fact that we can declare that an object isn't in rotation and that the rest of the universe is rotating around it. Well, what about the case of the Earth? It used to be believed that the Earth was fixed and the heavens rotated around it. And there was a guy named Galileo who came along and suffered greatly because he said, no, that's wrong. The Earth rotates beneath the heavens. And Mach would reverse all of that with his mind games. So I guess what I would say is, if you're working in physics and you still think there's some merit to Mach's principles, you might want to recheck your basics or question your life choices. In fact, in my opinion, Ernst Mach doesn't deserve to even step into the same ring with Isaac Newton. Now, around 1901, they began to award the Nobel Prize in physics and other categories. And the prize was given for someone whose work had provided the greatest benefit to mankind during the year. Well, if you go back and you think about any physicist who's ever lived, whose work has provided the greatest benefit to mankind, and it's overall, hands down, Isaac Newton. He created the Industrial Revolution. If it flies fast, if it drives, if it stands tall, it's the result of Newton's laws being applied by engineers. Everything we have today of a mechanical nature, and even a lot of cases the optical nature, derives from Newton's laws. So by far, I don't think there's another physicist who stands close to the benefit to mankind that's been provided by Isaac Newton. And that's something to think about. So until next time, I'm Hugh Mannfield.